Okay guys, so hopefully you have your guided notes with you so you can take notes as we go through the video, and please press pause as you need to if I am going too fast. So we're talking about area between two curves, and we've already discussed where integration is the area under a single curve. So if we think about, I want to find the area between these two curves, I'm talking about this area in red. Okay, and so if I just do the area under this top curve, here's my top curve, and keep in mind the red part stops here and here, so if I'm stopping here and here, if I just do that part, area under the curve, all right, then it's all of this stuff here. All right, so I don't want all of that. I don't want this blue stuff that's not overlapping the red. So we have to subtract this part right here. I'm going to shade in green. I want all this stuff in green to not be counted. Now all that stuff in green is the area underneath this bottom curve. So if I want to find the area between two curves, I'm really just going to take the area of the top curve. Let's call the top curve f of x. And then I'm going to subtract the area of the bottom curve. We'll call the bottom curve, call this one g of x. Oh, it's labeled there, g of x. Okay, so here's what we do officially. Okay, the area of a region between two curves. Notice in our definition that f and g are continuous on a closed interval from a to b. And notice that g of x is always less than f of x for all of your values in that interval. Then the area of the region is simply the integral from a to b of f of x minus g of x. Notice that we're talking about the area bounded by those graphs and in between those two vertical lines. Okay, so let's do an example. All right, so we want to find the area bounded by y equals x squared and y equals x plus 6. So first let's graph this. Y equals x squared is pretty easy to graph. And y equals x plus 6, so this is 1, 2, 3, 4, 5, 6, so looks something like that. So in order to find this area in between, first we need to know where to start and stop. So we need to find these points of intersection. Okay, so our points of intersection.
Ryan McCormick, please go to the attendance window.
I'm going to set those two things equal to each other and solve. Okay, so I'm going all the way from x equals -2 to x equals 3. So my graph was a little off. And notice that our top curve is always the line, the green line, so that's going to be our f of x. And then the bottom curve is always the parabola, so that's going to be our g of x, our bottom curve. Okay, so let's set up the integral. So we're going to say the area is equal to the integral from -2 to 3 of our f of x, which is x plus 6, minus our bottom curve, which is x squared. So all we have to do is integrate that. And since it's a polynomial, it's pretty easy to do the antiderivative. So we're going to have 1/2 x squared plus 6x minus 1/3 x cubed. And we're going to evaluate that from -2 to 3. So let's do that. Okay, so if I plug in 3, I'm going to get 9/2. Here I'm going to get 18. And then here I'm going to get, let's see, 3 cubed is 27 divided by 3, so minus 9. And then I'm going to plug in -2. So here I'm going to get 4 divided by 2 is 2, and then negative 12, and then let's see, 8/3, negative 8/3. No positive because I'll have a double negative. Okay, so here I'm going to get 13.5 minus, this is going to be negative 7 1/3. So if you wanted to, you can just keep it that way, or if you wanted to do a decimal, 20.83 repeating. Okay, that's the area. So our area is equal to this. Okay, so that's finding the area bounded by 2 curves. Now if we move on to the next example, we want to find the area between these 2 curves. And here's what I want you to notice. The parabola, that's this guy, goes like this. And then the cubic goes like this. So does anyone see a problem with this? If you haven't seen it yet, we have a break here to here. That's going to be that area. But then we have this tiny little sliver right here, right? And that's going from here to here. So do you notice in this big area, the blue graph is the top curve, red is the bottom, whereas in this little bitty sliver, the red is the top, blue is the bottom. So we have to split that up into 2 different integrals, okay? So we're going to do the big area. We have to find the points of intersection. Let's do that before I set up the integrals. All right, so we want to do x cubed plus x squared minus 7x minus 10 equals negative x squared plus 2x plus 8. All right, so combine all your like terms together. And I'm going to try factoring by grouping. So this is going to give me x squared, x plus 2. Factor out the negative 9. That gives me x plus 2. Hey, it works. So I'm going to have x plus 2 and then x squared minus 9. All right, so if I set this one equal to 0, I'm going to get x equals negative 2. Here I'm going to get x equals plus or minus 3. All right, so my points here, this is going to be x equals negative 3, this is x equals negative 2, and then this is x equals positive 3. Okay, so now we're ready to set up our integrals. So for that big area, I'm going to be going from negative 2 to positive 3. You know what, let's just work from left to right. I changed my mind. I'm going to go from negative 3 to negative 2. Okay, so I'm doing that little bitty tiny sliver. All right, so on that tiny sliver, remember that the red is on top, the cubic is on top, and the quadratic is on the bottom. So I'm going to be doing x cubed plus x squared minus 7x minus 10 on top. That's the first curve, minus the quadratic. All of that is with those limits of integration. Okay. All right, so let's do it. I know you guys are all groaning right now. That's okay. We can do it, right? So combine like terms first. All right, so I've got 1/4 x to the 4th plus 2/3 x cubed minus 9/2 x squared minus 18x, all from negative 3 to negative 2. Okay, so to save time, let's use calculator to plug in. Keep in mind though, AP, what they might do is they might actually have you evaluate things like this with fractions. So don't worry, don't be too lazy with fractions. All right, so I'm getting 16 2/3 minus 15 3/4, which is equal to 11/12, or as a decimal, that's 0.916 repeating. So do that yourself, make sure I'm right, and if I'm wrong, let me know next class. All right, so that's just the sliver. All right, now we're ready to do the big area. Big area goes from -2 to +3, and this time we're doing the parabola on top minus the cubic on bottom. All right, so combine our like terms again. And then do the antiderivative. Does this look familiar? So obviously it's just, since all we did was change the order, then it just changes the negatives around. So we're going to evaluate from -2 to 3. So when I evaluate for 3, I'm getting 56.25. When I evaluate -2, I'm getting -16.6 repeating. So that gives me 72 and 11/12, which is about 72.916 repeating. Okay, so we're going to take those two values together. So I've got the 72 and 11/12 plus just a little bitty sliver. And that gives me 73 and 5/6. Okay. So again, if you're having issues with that, let me know next class and we can go over that. And then our last example, we want to find the area between these two curves, and notice that we've got a sideways parabola, right, a conic. All right, so something I want you to think about is, you know, if I have area and we do the vertical rectangles for area and all that stuff like a Riemann sum, then yes, we're doing top curve minus bottom curve. All right, but I could make stack those rectangles sideways, and I could be accumulating area this way. So having rectangles look like this. Okay, so if that's the case, then I don't have dx, I have dy, right? So I'm going to be integrating with respect to y. And then I don't have a top curve and a bottom curve. I have the curve that's furthest away from the x-axis. That's what we call the right curve. All right, and then I have a curve that is closest to the y-axis. That would be like your bottom curve or your left curve. All right, so here, let me color code this a little bit. So this is the green is the left curve, the blue is or here, I'll make it red. The red is the right curve. Okay, so rather than having to split this up, because if I was doing it with vertical rectangles, I would have to split it up there. Okay, instead of doing that, we can just integrate with respect to y, and it becomes a lot easier type of problem. AP loves to do this, give you a problem that's very simple to do using integration with respect to y, and then it's really, really hard or almost impossible to do with respect to x. So I really want you to force yourself to get used to integrating with respect to y. Okay, so if we integrate with respect to y, then I want this second equation in terms of y. So I'm going to have x equals y plus 2. And then we're going to set these equal to each other. So y plus 2 equals y squared. We're trying to get our points of intersection. So I'm getting y equals -1 and y equals 2. So we're going from here at y equals -1 all the way up to here where y is equal to +2. So those are going to be our limits of integration. from -1 to 2, and then we're doing right minus left. So y plus 2 minus the y squared dy. Okay, and then the integration is a lot easier. Okay, so let's do it. So if I integrate that, that's going to be 1/2 y squared plus 2y minus 1/3 y cubed. Ooh, I'm sorry, that's a horrible 3. Evaluated from -1 to 2. All right, so I'm going to get 4, 2, so that's 2, and then 4, then -8/3 minus, I'm going to get 1/2 minus 2, and then plus 1/3. So this is 3 1/3. This is -1 1/6. So this is going to give me 4 1/2. Okay. So there we go. We found that pretty easily rather than having to split that up. Okay. All right, so there we go. You're going to have your homework to do for the rest of class. And next time we will review for your test.